Welcome and thank you for your interest and overwhelming response to the previous lecture. In actual, thousands of classic videos and literature on FEA are available. However, time constraints may not allow the read, learn and execution of theoretical research work. Considering this, I have compiled a few slides that may boost interest and understanding the importance of finite element analysis. In this lecture, I want to give much more emphasis on fundamentals and execution of finite element analysis. Finite element analysis follows a computerized numerical method for predicting how a product reacts to real world forces, vibration, heat, fluid flow and other physical effects. It shows whether a product will break, wear out or work the way it was designed. FEM reduces the degrees of freedom from infinite to finite through discretization or meshing. Meshing, while we are considering the meshing, two terminologies, nodes and elements are important. Let us consider this figure. In this figure, we can see these are the nodes and this is considered are elements. So, FEM cuts a structure into several elements, pieces of the structure, then reconnects elements at nodes through connection of all nodes together and we can get elements. This process results in a set of simultaneous algebraic equations. How we can get algebraic equations? We are coming into next slide. So, this is one example while FEA has been performed for different board dimension for shrouds and we can see there are different type of number of nodes and elements for 50 millimeter board diameter and 75 millimeter board diameter, while the dimension is more, total area is more and number of nodes and elements both are more. So, degrees of freedom is very important concept in FEA. It is usually used for the individual calculation points. In brief, minimum number of parameters, motion, coordinates, temperature, etc. are required to define the position and state of any entity completely in space is known as degrees of freedom. In simple, if we consider a two-dimensional rectangle and if point A, the movement of A, it may be x direction or y direction and with having one rotational direction. So, 2 plus 1, but when 2D converted to 3D, there is the possibility of 3 translation and 3 rotational motions. So, that is why it cumulative 6. So, the number of DOFs depends on the type of elements 1D, 2D, 3D, the family of element, thin cell, plane stress, plane strain, membrane, etc. and the type of analysis, static or dynamic analysis. Total DOFs for a given mesh model is equal to the number of nodes multiplied by the number of DOF per node. So, if we take this example, here number of nodes are infinite and DOF per node is 6. Then total number, if we multiply these two, then the total number of equation becomes infinite. But if we consider this one, the number of nodes are predefined 9 and DOF per node is 6. So, total equation becomes 54. So, finite element method only make calculations at a limited number of points and then interpolates the results for the entire domain. It may be surface or volume and we can obtain the accurate result. The concept of boundary conditions is very important while we want to analyze a perfect model. So, in brief, real life conditions translation into a digital representation without simplifying it too much. This actually represents how you are considering the boundary conditions to analyze your developed model. Here let us consider one model, magnesia carbon brick as model, and if it falls down and hit the surface, how it falls, it may be, that means what would be the motion of the brick, how is it under gravity or under defined velocity. So this would be the boundary condition, and it will hit the surface. Since surface is not penetrated, because of that it's considered a 2D cell, and we can estimate the impact. So that means this is the model, this is the boundary condition. So we have to consider the 2D cell, and we can get the influence of the impact, and during this contact we can get static and dynamic coefficient of friction of while both brick and floor are in contact. In another example, 3D printed implant where material has been developed and employed 3 megapascal pressure and estimated the maximum stress and deformation. If we extrapolate this line, we can see this is the point where maximum deformation and this is the minimum deformation. Here 3 megapascal pressure has been employed and with these fixed conditions. So these are the boundary conditions actually considered to develop this 3D printed implant. How it solves? Many engineering phenomena can be expressed by the governing equations, that is differential equation plus boundary conditions according to our objective, and at the end of day we can get algebraic equation and it's converted through FEM. So if we consider a simple equation, F is equal to KU, F is equal to action, K is equal to material properties, and U is the displacement, that is unknown behavior. So while F is employing on certain material, and we can get the displacement. So from this equation we can get the unknown parameter displacement. This is usually unknown. So it is very difficult to make the algebraic equations for the entire domain. Okay, so divide the domain into a number of simple elements like this. Adjacent elements share the DOF at connecting nodes, as we discussed in previous slides. This is the nodes and DOF is there. A field quantity is interpolated by a polynomial over an element. Put all the elements equations together. So if we want to get the effect of the entire domain, we have to add all equations and we have to solve it. So that means if it is property, F is the action and U is the behavior. So if we employ some action on material with having known property, we can find out the behavior. So this is the stiffness matrix for rod elements through direct method. This is simple one. If you put the stress along the x-axis, you can get this is your force. A is nothing but area, elastic modulus, L is length, and we can get the force matrix, stiffness matrix and displacement matrix as like F, K, U. And if it is two rod elements with having different properties, and we can add and we can get the matrix. So FEA procedure by commercial software, it has three important steps. One is pre-processing, process and post-processing. Among these three, user has to complete 1 and 3 and computer 2, process 2. So in process 1, the purpose and input, material definition, meshing, loading and boundary conditions need to be employed, and command file, formation of command file, and computer will get the numerical analysis and we can get different parameters, stress, strain, graphs, displacement, all those. In next slide we can get much more details idea, while we entire process has been discussed through steps. Step 1, select analysis type, what sort of analysis you want to do for a particular material or model. Select element type, it is 2D or 3D, material properties, elastic modulus, Poisson's ratio, density, coefficient of thermal expansion. Make nodes, build elements by assigning connectivity, apply boundary conditions and loads. Then solve the boundary value problems by system or computer. See the results post process, and it may be displaced, stress, strain, natural frequencies, temperature, time history, depends on your demand and your input. Meshing accuracy has significant influence on the resultant accuracy or analysis. Let's consider one circle in which if we put one triangle, the most of the part has not been covered, but while it is converted to 3 line to 4 line and followed by 6 line, 8 line, we can see that this area minimum. So that means maximum area has been covered and we can get more accurate results. So when the number of lines more and more, the accuracy is more. But when number of line more, so that means we can employ the more number of mesh. So more lines, more elements, more solution time and more accuracy level. And when we are considering the more accuracy level, we need high RAM and more time. So that is why in industry most of the time people are considering the range in between 90 to 100% accuracy with minimum time. So that means in brief, if we consider this is mesh, so this is only here covered only 4 elements, but if we put number of elements more, so the accuracy more, and the number of equations here is 16, so almost here is 4 times, so number of equations more and accuracy more. So in brief we can say if the number of line more, the accuracy more, but we need more time and high sophisticated computational facilities. So in the similar fashion, if we consider one 3D model, and if this zone is equal to this zone in 2D representation, and if 2 element along radius, we can see these are some vacant area. But when we convert it to 2 to 4, 16 element along radius, we can see most of the zone has been covered, and if we analyze the stress on this zone, we can accurate result here compared to this one. So that is why it is required to judge and select number of elements judiciously and you have to synchronize properly time as well as accuracy. In here also we have to judge the both input and output properly to interpret the result and the outcome. This is some simple example which has been published by my BTech student. We tried to develop knee prosthesis by 4 model and 5 different material. Here we consider 4 model and 5 different materials. So that optimization of material and model. Here we can see there is gap between 2 part. This is continuous, this is gap and protruded, this is continuous and protruded. So and we consider 5 materials among this ZTA, and connected and protruded part was optimized in the perspective of stress, strain, deformation, all those. Here we started all those analysis through the pre-process process and post process. More details can be found here. In another literature, the thermal mechanical stress analysis of ladle lining with integral brick joint has been studied. In this heat transfer model of ladle was developed, then different material input was given, then developed the model and analyzed. The expansion joint in 2 bricks has been optimized through FEA between 2 bricks. So, expansion joints between 2 bricks has been optimized, and within 0 to 4 different value was taken and 2 millimeter was optimized, where the expansion joint is set to 2 millimeter to avoid steel leakage and guarantee the safe production of the steel in the making process. So, that is all. Next lecture I will discuss on CFD in the perspective of refractory development. Thank you very much for your patience.